My name is Madhuri Gupta, Assistant Professor, Department of Computer Science, Chhattisgarh Swami Vivekanand Technical University, Bhilai. In today's topic, we will cover about union and intersection in Prolog. Before that, let's have a quick recap on our last lecture on recursion. Recursion in Prolog. Recursion is a fundamental concept in Prolog, a logic programming language. In Prolog, a predicate or function can call itself within its own definition. This allows you to solve problems that can be naturally expressed in recursive terms such as traversing data structure like list or trees. Here are some key points typically covered in lecture on recursion in Prolog. Base case. In a recursive predicate, you need to define a base case that specifies when the recursion should stop. The base case is essential to prevent infinite recursion. Next, recursive case. The recursive case describes how the problem is broken down into smaller similar subproblems. In Prolog, this typically involves making recursive calls with modified arguments. Next, backtracking. Prolog uses a depth-first search strategy with backtracking to explore the solution space. When a recursive call fails, Prolog backtracks to the previous choice point and explore alternative solutions. Next is accumulators. In many recursive Prolog predicates, accumulators are used to accumulate intermediate result. This is often necessary when processing list or performing arithmetic operations. Next, we have covered tail recursion. Tail recursion is a specific form of recursion where the recursive call is the last operation performed in the predicate. Prolog optimizes tail recursive predicates, making them more efficient. List processing. Recursive predicates are commonly used for list processing tasks like appending list, reversing list or finding elements in the list. Examples problem. A lecture on recursion in Prolog which include examples of solving problem using recursion such as computing factorial, calculating Fibonacci series or traversing binary trees. Debugging and trace. Understanding how to debug recursive Prolog predicates including using the trace functionality is an important part of learning recursion in Prolog. It is important to practice writing and understanding recursive predicates in Prolog to become proficient in using this powerful feature for problem solving. This specific content of your last lecture may have covered one or more of these aspects in more details or introduce additional concepts based on your course curriculum. Now, in today's topic, we have to cover union in Prolog. In Prolog, you can define a predicate to find the union of two lists. The union of two lists is a new list that contains all unique elements from both input lists. Here are 5 examples of how to find the union of two lists in Prolog. Basic union predicates. Define a predicate to find the union of two lists. So, how you can define it? Union in a fact form or in a relation, then you have to in a parenthesis you have to define empty list, then list comma list, then union head tail comma list to result, which implies member of head list 2. That means check if head is in a list. Next, cut to prevent backtracking. How we can define it? Union tail list to result, union head tail comma list to head result implies that union tail list to result. So, how we can use it in Prolog? you have to query about union in a first list 1, 2, 3, then in a again another list 3, 4, 5 and the result. So, result will be equal to 1, 2, 3, 4, 5. So, we have united the whole 2 list. Next is union of empty list. Query union empty list, then the result. So, result will give you the empty list. Next is union with one empty list. So, the query will be 1, 2, 3 in a one list, comma empty list, comma result. So, the result will be 1, 2, 3. Next, union with duplicate elements. So, we have to query about 1, 2, 3, comma 3, 2, 2, 4, comma result. So, the result will be 1, 2, 3, 4. The next type of union, union with list of atoms. So, how you can query about union apple, banana, cherry, comma cherry, comma date, comma apple, comma result. So, the result will be banana, cherry, date and apple. So, these examples demonstrate how to use a basic union predicate to find the union of two lists in Prolog. The predicate checks for duplicate elements and ensure that the resulting list contains only unique elements from both input lists. Now, intersection in Prolog. In Prolog, you can define a predicate to find the intersection of two lists. The intersection of two lists is a new list that contains all elements that appear in both input lists. Here is an example of how to find the intersection of two lists in Prolog. So, in Prolog, define a predicate to find the intersection of two lists. Intersection, then empty list, then you have to define the, if the first list is empty, the intersection is also empty. Then the next intersection head tell, comma list 2, comma head result, which implies member of head, comma list, which means if head is in list 2, include it in the result. So, intersection tell, comma list 2, comma result. Intersection head tell, comma list 2 result, which implies member head, comma list 2. That means if head is not in list 2, skip it. Intersection tell, comma list 2, comma result. So, how we can use it? So, you have to query about intersection 1, 2, 3, 4 in a one list, comma 3, 4, 5, 6 in another list, comma result. So, the result will be 3, 4, the common of both. Now, the next query will be intersection in one list apple, banana, cherry, comma in another list cherry, date, apple, comma result. So, the result will be apple, comma cherry. So, in the code above, the intersection predicate takes the three arguments to list and the resulting intersection. If the first list is empty, the intersection is also empty. If the head of the first list is in the second list, checked using member of 2, it is included in the result. If the head of the first list is not in the second list, it is skipped. Recursion continues until both input lists are fully traversed. This predicate finds the common elements between two lists, preserving their order in the original list. Certainly, here are 5 more examples of finding the intersection of two lists in Prolog. First, intersection of empty list. So, the query will be intersection empty list, then empty list, comma result. So, the result will be empty list. Second, intersection with one empty list. So, you have to query about intersection in a one list 1, 2, 3, comma empty list, comma result. So, the result will be empty list. Next is intersection with no common elements. So, you have to query about first list 1, 2, 3, comma 4, 5, 6, comma result. So, the result will be empty list because there is no common element. Next type is intersection with duplicates. So, you have to query about intersection 1 2 2 3 3 4 comma 3 4 4 5 6 comma result. So, the result will be 3 4. Next type is intersection with list of atoms. So, you have to query about apple, banana, cherry in one list, comma cherry, date, orange in one list and result. So, the result will be cherry. These examples demonstrate how the intersection predicate works in Prolog to find the common elements between two lists, handling various scenarios including empty list, list with no common elements and list with duplicate elements. Now, how to solve water jug problem in Prolog? The water jug problem is a classical puzzle that involves two jugs of different capacities and a desired target volume of water. The goal is to find a series of actions, that means pouring water into or out to the jugs to reach the target volume. You can solve this problem using Prolog by defining the problem constants and writing rules to find a solution. Here is an example of how to solve the water jug problem in Prolog. So, first of all, define the capacity of two jugs. So, for that we have to define the function like jug capacity in a bracket jug 1 comma 4, and again the next function is jug capacity jug 2 comma 3. So, we have capacity of jug 1 4 and jug 2 is 3. Next is define the initial state with both jug empty. So, initial state jug 1 comma 0, initial state jug 2 comma 0. Next step is define the target state with a specific amount of water in one of the jugs. So, we have to define the function like target state, target jug comma target volume, which implies jug capacity, target jug comma capacity. Target volume is greater than equal to 0 comma target volume is equal to less than capacity. Next, define the possible action to pour water from one jug to another. Pour state 1 comma state 2 comma action, which implies state 1 represent the current state and state 2 represent the resulting state. So, state 1 is equal to jug 1 volume comma jug 2 volume comma state 2 is equal to new jug 1 volume comma new jug 2 volume. And how to define the action represent the pouring action, that is pour jug 1 comma jug 2, means pouring from jug 1 to jug 2. So, our action is equal to pour jug from comma jug 2. Jug capacity jug from comma capacity from, jug capacity jug 2 capacity 2. Now, pouring from jug from to jug 2. First, calculate how much can be poured. Second, update the volume in both jugs. Third, ensure that jug 2 does not overflow and jug from does not become negative. Pour amount is minimum jug volume comma capacity 2 jug 2 volume comma new jug volume is jug 1 volume minus pour amount, new jug volume is jug 2 volume plus pour amount comma new jug 1 volume is greater than equal to 0 comma new jug 2 volume greater than equal to 0. Next step is define the goal state, that means reaching the target volume in a specific jug. So, goal state implies that target state jug comma target volume comma member of jug target volume comma state. Next step is define a recursive predicate to find a sequence of action to reach the goal. Solve state, state, comma empty list. Solve current state, final state, then the action, which implies pour current state, comma next state, comma action. Solve next state, comma final state, comma action, full stop. Next step is define a predicate to solve the water jug problem. Solve water jug actions, which implies initial state, comma target state, in a bracket target jug, comma volume, target jug, comma target volume. Solve initial state, comma final state, comma actions, which define the goal final state. Then write ln solution in a single quote, then print action actions and format reached negative w with negative w, literals in negative w, target jug, target volume, target jug. Next is define a predicate to print a list of actions. Print actions in an empty list, print action, action, rest, which implies write ln action and print action rest. You can use the solve water jug actions predicate to find a solution to the water jug problem. For example, in Prolog you have to query about solve water jug and actions. This code defines the problem, initialize the state and finds a sequence of actions to reach the desired target volume. It also prints the solution steps. Now, our next problem is family hierarchy problem in Prolog. So, how we can solve the family hierarchy in Prolog? Solving a family hierarchy problem in Prolog typically involves defining facts and rules to represent the family relationship and then querying the knowledge base to answer specific questions about the family. Here is a step-by-step guide on how to solve a family hierarchy problem in Prolog. First, define facts. Start by defining facts to represent the family members and their relationships. For example, facts representing family members. So, male in a parenthesis John full stop, that means male is John, John is male. Then male Bob, female Linda, female Suzanne, parent John, comma Bob, that means John is a parent of Bob. Then parent Linda, Bob, that means Linda is a parent of Bob. Then parent John, Suzanne, that means John is a parent of Suzanne. Then parent Linda, comma Suzanne, that means Linda is a parent of Suzanne. In this example, we have defined family members, their genders and parent-child relationships. Next step is define rules. You can define rules to infer additional relationships such as sibling, grandparent or aunt-uncle relationships. For example, rule to define siblings. Siblings x comma y, which implies that parent z comma x comma parent z comma y comma x or equal to y. Next is rule to define grandparents. So, grandparents x comma y, which implies parent x z comma parent z comma y. These rules use parent-child relationship to deduce sibling and grandparent relationships. Next is query and knowledge base. Use Prolog queries to ask questions about the family hierarchies. For example, we have query like who are the siblings of Bob. So, you have to query about sibling Bob comma x. This will give you the result about x. Prolog will provide answer based on the defined facts and rules. Next step is add more facts and rules. Extend your knowledge base with additional facts and rules to represent more complex family hierarchies or answer more specific questions. For example, you can add facts for marriages, aunts, uncle and cousin, etc. Next is fact representing marriages. For example, married John, Linda, married Suzanne, Mike. So, we have to define the rules to define aunts and uncle, aunt or uncle x, y, which implies parent z, y, sibling x, z. Now, continue querying. You can now ask more specific question about the family hierarchy taking into account the new facts and rules you have added. So, you have to query who are the aunts and uncle of Bob. So, you have to ask it like aunt or uncle x, Bob. So, you will get the answer as x is equal to whatever the answer of uncle or aunt. Next is experiment and explore. Use Prolog's query capabilities to explore various aspects of family hierarchy such as finding all cousins, determining relationships based on gender and more. Remember that the specific facts and rules you define will depend on the details of the family hierarchy problem you are working on. By iteratively defining facts and rules and querying the knowledge base, you can navigate and solve various family hierarchy problem in Prolog. Now, our next example is how to solve the A star algorithm using Prolog. Solving the A star algorithm using Prolog involves defining predicates for representing the problem, heuristic and search algorithms. A star is used to find the shortest path from a start state to a goal state in a weighted graph or grid. Here is a step-by-step guide on how to implement the A star algorithm in Prolog. Step 1. Define the state representation. Define the representation of a state in your problem domain. This should include predicates for representing the current state, successor state and the goal state. For example, you are working with a grid. You might represent state as x, y coordinates. So, in Prolog you have to write example state representation for a grid, state x, y, goal state goal x, goal y. Next step is define the actions. Define the actions or transitions that can be applied to move from one state to another. This action should be represented as predicates. For example, actions for a grid: move state x, y, state new x, new y, which implies define valid movements. Here new x is x plus 1 and new y is y. Now, our third step is define cost. Assign cost to actions or transitions between states. You can use predicate to represent the cost of moving from one state to another. In Prolog, you have to write example cost function for a grid. So, you have to define cost state x, y, state new x, new y, cost, which implies define cost computation here. Cost is 1. That means, for example, a constant cost. Next step is define the heuristic. Define the heuristic function that estimates the cost from the current state to the goal state. This function helps A star prioritize which state to explore first. In Prolog, you have to define the example heuristic function for a grid. Heuristic state x comma y comma h, which implies goal state goal x comma goal y comma h is a absolute x goal x comma h is absolute x minus goal of x plus absolute y minus goal of y. Next process is implement the A star search algorithm. Define the A star search algorithm using predicates. You can use a priority queue or other data structure to keep track of states and their associated cost. So, in Prolog, A star start comma path, which implies empty PQ, empty PQ comma add to PQ, start comma 0, empty PQ comma PQ comma A star search, PQ comma empty list comma path, A star search, PQ comma visited comma path, which implies implement A star search here. Check if PQ is empty or if the goal state is reached. Expand nodes, calculate cost and add to PQ. Update visited list. Continue searching. Our next step is retrieve the optimal path. Once the A star search algorithm finds the goal state, retrieve the both optimal path by backtracking through the parent state. In Prolog, you have to write it retrieve path visited comma start comma path, which implies implement path retrieval here by backtracking through visited. Now, our next query will be query the A star algorithm. Query the A star algorithm with the start state to find the optimal path. In Prolog, you have to write in a query A star start state comma path. Now, our next step is test and experiment. Test your implementation with different start and goal state and experiment with different problems, domains and heuristic to solve various A star search algorithms. Keep in mind that this is a high level outline and the specific predicates and implementation will depend on the details of your problem domain. The key is to represent the problem in Prolog terms, define actions, cost and heuristic and implement the A star search algorithm accordingly. Now, our next problem is the block word problem. The block word problem typically involves arranging blocks with letters on them to form a specific word. Each block has a set of letters on its sides and you need to determine the sequence in which to place the blocks to spell the target word. Here is a simplified example of how to solve a block word problem in Prolog. Let us say you have 3 blocks with letters on their sides. Block 1 A, B, C, block 2 D, E, F, block 3 G, H, I, and you want to spell the word beg. You can represent the problem in Prolog as follow. First, define the blocks and their letters. Block 1 in a list A, B, C, full stop. Block 2, 2 comma D, E, F in a list, full stop. Block 3, 3 comma G, H, I, full stop. Now, the next process is define the target word. So, target word in a list B, A, G, full stop. Now, the next process is predicate to find a valid arrangement of blocks to form the target word. Arrange blocks. So, in an empty list you have to define the in parenthesis 2 empty list. Then arrange blocks, target word, block arrangement, which implies select letters, letter, comma block, comma remaining letters. Select letter, comma target word, new target word. Arrange block, new target word, comma arrangement. Now select a letter from the block and get the remaining letters. Select letter, letter, comma, letter and rest, rest, select letter, letter in an empty list, then rest remaining letters, which implies select letters, letter, rest remaining letters. Now you can use the arrange blocks predicate to find a valid arrangement of blocks to spell the target word. In Prolog, you have to query about target word, target, comma, arrange blocks, target, comma, arrangement. Prolog will provide a solution that shows the sequence of blocks to form the target word. This is a simplified example and you can make it more complex by adding additional constants or rules based on your specific requirements. Depending on the complexity of the block word problem, you may need to design more sophisticated algorithm or heuristic to find the optimal arrangement of blocks. Now our next example is the monkey and banana problem. Is a classic puzzle where you have a monkey, a banana and a box. The monkey is initially at the door. The banana is hanging from the ceiling and the box is on the floor. The goal is to move the monkey to the banana, grab the banana and then get back to the door using a sequence of actions. These are certain rules governing the actions. First, the monkey can only hold one item at a time. That means either the banana or the box. Next step is the monkey can climb the box. Next step is the monkey can push the box, but only if it is not holding the banana. You can solve this problem using Prolog by defining the initial state, goal state and valid actions and then searching for a sequence of actions to reach the goal. Here is an example Prolog implementation. So, in Prolog, define the initial state to the problem. Initial state at monkey, comma door, comma at box, comma floor, comma at banana, comma ceiling, comma on floor, comma box, comma not holding monkey, full stop. Next step is define the goal state. Goal state monkey, comma banana, comma at then in a bracket banana, comma empty, then the bracket close, then comma, then the bracket close. So, next step is define valid actions that can be taken in the current state. Each action has a precondition and a resulting state. Here we define actions for climbing the box, pushing the box and grabbing the banana. Note that we also have to specify when actions are possible. Monkey can climb the box if the box is on the floor and the monkey is not holding the banana. So, action will be action climb box, comma on floor, comma box at monkey, comma door not holding monkey, comma on box, box at monkey, comma box not holding monkey. Now, monkey can push the box if the monkey is at the box and not holding the banana. So, action is push box, comma at monkey, comma box not holding monkey, at monkey door not holding monkey. Monkey can grab the banana if the monkey is at the banana and not holding anything. So, action is grab banana at monkey, comma banana, comma not holding monkey, holding monkey, comma, banana, then full stop. Rules to check if an action is possible in the current state. Possible action, comma, state, which implies action, action, comma, preconditions, subset, precondition, comma, state. Now define a predicate to apply an actions and transition from one state to another. Apply action, action, comma, state, comma, new state. That means action, action, comma, new state, comma, effect. Then subtract state, comma, effects, intermediate state, comma, union, intermediate state, effects, new state. Next step is define a predicate to find a sequence of actions to reach the goal state. The plan is a list of actions, plan, state, comma, goal, comma, plan, which implies plan, state, comma, goal, empty list, then plan. Base case: when the current state is the goal state, the plan is empty. Plan, state, state, comma, plan, comma, plan. Recursive case: find the next action that can be applied and continue planning. Plan, state, comma, goal, comma, current plan, comma, plan. So, possible action state, apply action, action state, new state, plan, new state, goal, action, current plan, comma, plan. Define a predicate to execute a plan and obtain the final state. Execute plan, state, empty list, then state. Execute plan, state, action, rest, comma, final state, which implies apply action, action, comma, state, new state, then execute plan, new state, comma, rest, comma, final state. Now you can use this code to find a sequence of action to solve the monkey and banana problem. For example, in Prolog you have to write about the query initial state, in initial state, comma, goal state, comma, plan, initial state, comma, goal state, comma, plan. This will find and display a plan of action to solve the problem, moving the monkey to the banana, grabbing the banana and returning to the door. So, thank you so much, and we will see you in the next lecture, which is the summary of the course. Thank you so much.